In this lecture, we study artificial neural networks. First, we will consider the structure of artificial neural networks. It is constructed from basic blocks using the simple model. Similarly, a simple model that is very similar to the perception model we discussed in our last lecture. And then we will consider the main point of today's lecture, that is the training algorithm of a neural network. Learn its way to adjust the model parameters to navigate in the hypothesis space so that the model fits the data better. And I will show an example of implement such an algorithm on a computer. Also, we will discuss some issues, practical issues of the training algorithm. Then comes to the other strand of our tale of the two cities. That is why learning is possible. Last time we have discussed that learning is possible because it is unlikely that you have bad generalization errors while have the good in sample assessment, but that doesn't apply to multiple hypotheses. Today we'll discuss the case of multiple hypotheses, or even hypothesis space that contains infinite number of hypotheses. Okay, let's begin with constructing neural network using perceptions. First, have a look at the perception model. It has some input, taking the weighted sum of the input and generate an output. In a neural network, we employ multiple perceptions and give the input to all these perceptions. For example, take that as a perception unit group 1. After this group of perceptions takes the input and generates their output, we take their output into the next group of the perceptions. So we have this computational scheme proceed similarly for multiple times. That is the computational model of neural network. Before we get into the details of the network construction, let's have a look. Let's view the difference and similarity between a perception and a neural network from the light of the learning framework. Both models have a number of real numbers to describe the model. They are both specified by the weight parameters, so the hypothesis space are similar between two models. In this aspect, you can think perception is an extremely simple neural network. It is a special case of neural network. However, they have some more fundamental difference. Okay, here is a similar element. The difference lies in the learning algorithm and the measure of misclassification, or the loss, or the risk. In perception, the risk is measured by how many samples are misclassified. This risk jumps in the perception, in the hypothesis space of perceptions. For some of the hypotheses, you have, for example, certain number 5, 4, 7 misclassifications. For the other hypothesis, you can suddenly move from like have 5 errors to 6 or to 4. And the learning algorithm adjusts the weight vector by aligning it to the misclassified samples, and the alignment goes in discrete steps. But in neural network, from the view of training, that is very different. We will employ some loss that is continuous with respect to the hypothesis space, and employ some training algorithms that adjust the hypothesis smoothly to fit the model, which we will see later. The building block of a neural network is perceptions. Actually, neural networks have another name of multi-layer perceptions, which I find is not 100% accurate, but at least it provides us a very intuitive understanding of how a neural network works. Now let's take perception. The perception model we have discussed last week as the building blocks. To view it as a building block, we consider it as a black box. As a black box, focus only on its input and output of the model, right? Now we have the output of a perception here, and a perception has multiple inputs. Okay. The powerful idea behind neural networks is to adopt what I call a recursive design. So by recursive design, in particular, I mean that instead of taking every input of this perception black box from the data, we can consider the input is actually connected to the output of another perception model, right? Here is the out of this perception, but it is taken as the input of the perception of our concern here, and goes the same here. So we have multiple perceptions serve at the pre-processing unit for this unit in the center, and all their outputs are connected to the input of the central perception here. The same idea can be carried out to another another step. We can connect the output of the perception of our concern to the input of further perceptions. For example, here is one of its input, right? And it can be connected to simultaneously to multiple further layer perceptions. Now let's look at how the information is processed in this network. Remember, internally in the perception, each input is given a weight. Okay, let's call now, because of this input and output connections, we can group our perceptions into different layers. Those different groups of perceptions represent different stages of the computation. For example, if I write the perception of our main interest, the Lth layer, and the previous one take it as L-1th layer, and the next one L+1. And in each layer there can be multiple perceptions. Let us index this particular one, the ith perception of the Lth layer. Okay. Now consider its width associated with its impulse. let the weight be W of the ith perception of the Lth layer connected to the first perception of the previous layer. Okay, let it to be the first perception, and go all the way to the weight of the ith perception of the Lth layer to the let's call it pth perception of the previous layer. In practice, there can be different numbers of perceptions in different groups or layers. So we can write here, we can give P an index as well. So this is PL minus 1, means that is the number of perceptions of the L minus 1th group or layer. But here for clarity, let's remove this subscript first for the time being. Okay. Let's sum up the computation for the ith unit of the Lth layer, how it collects information from the previous layer. And this is the first perception of the previous layer that is associated with W of the Lth layer. Actually, you can write this W as how to connect L minus 1th layer to the Lth layer, but that is not necessary. So for clarity, we just write it as the width of the X layer. For the ith perception of the Lth layer, let's make it very explicit. Okay, and connect to the first neuron or perception of the previous layer. Okay, then we do the summation. Similarly, the second neuron of the previous layer of W of this layer, ith neuron connect to the second output of the previous layer. Do this all the way until we reach the pth and the last neuron of the previous layer. The ith perception of the Lth layer connect to the pth of the previous layer. Okay. What do we represent this sum as a result of this sum? Right? That is the x of the ith perception of this Lth layer. Okay. However, that representation of the operation is too mouthful for us to comfortably discuss how neural networks in a later stage. So for our convenience, let us reformulate this operation in matrix and vector form, which will turn to be very convenient later. Okay. Let us write those x in a row. X for L minus 1, first one, and x of L minus 1, the second one, this x p of L minus 1's layer. And if I write W, those width in a column, W for the ith neuron, connect to the first x of the Lth layer. W for the ith neuron of the Lth layer connect to the second second neuron of the previous layer, okay, go all the way to W of the ith neuron else layer to the connect to the last neuron. If we write this way in this row, okay, actually we can remember that the computation, the linear combination of these two sets of numbers can be written as an inner product, or in a matrix form we can write it as the x vector, which is the row vector, multiplied by this w vector, which is the column vector. Let's write it here. X L minus 1, this vector, which is a row vector, remember, multiplied by this W L I, which is a column vector. This is to write here temporarily. But remember, in each of the layer there can be multiple neurons. So instead of satisfying with now, we can compute the combination for the ith neuron of the lth layer. We can write the computation for all the neurons on in the lth layer altogether. If we write another column vector here, W I plus 1th neuron of lth layer and connect to the first neuron of the previous layer, and here Wi plus 1th neuron of the lth layer connect to the second neuron of the previous layer, go all the way here, Wi plus 1L, and connect to the last neuron. Okay, so if we repeat this practice for all the neurons in the lth layer, now what we have a matrix of the width or coefficients of all the neurons in the lth layer. Right, this matrix, okay, I can collect those column vectors. Remember, those are column vectors here. W, L, L, I plus 1. Let's call it W, L. Now we can see the computation actually write X L minus 1 multiplied by WL, and that is given to the output of the layer of the lth layer. Moreover, if you have multiple instances, instead of processing one sample at a time, using this representation, we can bite multiple samples together. X1 L minus 1, but this is the first row. Let us call it the second row, and that is X2 L minus 1 until XP L minus 1. But remember, this is another row. Okay. If we have multiple rows of that, like you have n rows, now you can have a X matrix, which is M by P of L minus 1, and multiplied by this W matrix L. This is given to the output, the result of the neural network of the lth row, the lth layer. In this notation, in this notion, we can view the computation of a neural network in a very concise way. Let the input data be x of the zeroth layer. That is the raw data without any processing. It is multiplied by W1. Remember, 1 means the transit from the zeroth to the first layer. Now we arrive at x1, which is then in turn multiplied by W2. Got x2 multiplied by W3, go all the way until we have the result of sum like XL as the final output of the network. But here we have a problem. Let's have a look. In this form, we can write the final output XL equals X0 multiplied W1. The result is being multiplied by W2. The result is being multiplied by W3. But we can change the order of multiplication. X0 multiplied by W1, W2, W3, go all the way, WL. If you call that W net, XL equals X0 multiplied by W net. But here is a problem. Previously, we designed a network. Okay, this is the input of the neurons of the data, and this input is processed and then represented by a set of neurons of the first layer, and then into neurons of the second layer, go all the way until neurons of the 11th layer represent our final output. But now, with this representation, actually, we squeeze all the network into a very simple one. Here is X0, and remember that one layer of computation can be represented by a matrix multiplication. Correspondingly, we can reverse this interpretation, and matrix multiplication can be can be implemented by one layer of neurons. Now directly we derive over XL. So the network collapsed. The key we are missing is here. In fact, the output of a perception is not quite just the same, just the summed, weighted summed input. If let's recap the structure of a perception like that, given this W's, and that is the input of this perception. From here, we have another unit. In the last lecture, this unit just dichotomized what is input according to threshold. Okay, it's either to be +1 or -1. Sorry, -1. But the value of this output is not important. The important thing is here this unit must represent some nonlinear relationship. Consider it more carefully, like the input of this unit is the weighted sum. We compute here. Let's plot them in horizontal axis, and let the output of this unit to be represented in the vertical axis. So if we directly write the output of the whole unit as a summed weight, this unit is the trivial passing over from the input to the output, where we have this curve. This identical curve. Whatever input is, the output is the same. The nonlinearity here means no, the linear, if you have the identical curve here, we have seen that the whole network will collapse. So for the nonlinearity, we need something like this, or different shapes of the curve can be employed for the nonlinear function. Whatever nonlinear relationship we employ in this unit, those relationships are inserted into this computation. Let's represent it using phi. Here is a phi here. This another phi, another phi. This is no longer equal to this expression, and the network now has a structure without being collapsed. So when you read the research of neural networks, sometimes you will find people take a great lengths discussing very simple functions like that. You may wonder why it is worth it talking this trivial relationship. No, they are not that trivial. They are, in fact, this is a calcium of the bones of your network. Without them, your network will fall together into, well, this very simple two-layer structure. With them, the network has powerful capacities of representing relationships. In fact, it has been proven that with only one layer between the input and the output, normally people call them hidden, because from the user's point of view, these layers are transparent to them. The user only can see the input and the output. Whatever computation stage is inside is hidden from them, so they are called hidden layers. With one hidden layer of neurons between the input and the output, you are able to simulate whatever function you want to. You are able to approximate whatever function you would like to target. Also, recently, it is found that if you have multiple hidden layers, the capacity of the network grows exponentially. But this is an open research topic, and it is very active recently. The training of the neural network. To discuss the training of neural network, we first need to know what is the goal of training a neural network. Of course, it is to feed the data. But as we have mentioned above, to feed the data, here we have an objective function that is different from perceptions. That must be smooth, not necessarily smooth, but it's continuous with respect to the hypothesis of the neural network. For example, if the task is to approximate some real-valued function, we may take the difference between the output of the neural network given the data and compare to the target value. For example, that square loss. Or if the problem is a classification problem, we may want to consider the output of the neural network as the probabilities of the input sample belonging to whatever category of the classes. In this case, we can compare the output distribution with the empirical distribution or the frequency we observed in the samples, and compare the divergence between the two distributions. We will consider this in the next lecture, but here is just a matter of two different distributions. Or if it is a binary classification value, we can take the simple way, like just having a switch If the target value is 1, we consider such a loss, and if it is 0, we consider the other loss. We will come back to this loss later in the programming demo. Okay, when we have defined the loss function, we will be able to calculate if we change the parameters of the network with by some infinitesimal amount. How will the change incurred on the object function will be? With that information, we can adjust the model parameter accordingly. The backpropagation training algorithm works can be demonstrated by this illustration. The workflow is first given the data, using the network to prepare information and compute the intermediate result in different stages, go so on and so forth to propagate. We can call that a forward propagate the information to reach the prediction. Then bring the ground truth in the supervision and compare the prediction and the ground truth using the loss. Now we have the knowledge of how about the output of the network changes. If we want to minimize the loss, we can back propagate this knowledge backward to all the elements in the network to know that for each of the elements, including the intermediate result and more importantly the model parameters, how to change those elements so that the loss function is changing accordingly. Okay, that's the principle of back propagation. We mentioned earlier that to do the backpropagation and compute how to train a neural network, we need a continuous loss function with respect to the network's hypothesis. We also will need some concrete function for the nonlinearity. So we introduce one here. But the specific form of this nonlinearity doesn't really matter in the backpropagation algorithm. The only essential requirement is that we are able to calculate how the function changes infinitesimally with respect to its input. Let phi a be 1 over 1 plus exponential minus a here. Oh, okay, let's consider this function a little bit closer, and let this be a. Oh, if when a is very small, for example, minus 999, okay, and this becomes very huge, and the bottom part of this number is very big, but the ratio becomes will be approaching 0. So when let here be 0, when a goes to small, the value becomes small. Okay, so when a equals 0, this phi a is 1 over 2, just in the middle between 0 and 1. Okay, and when a is very large, exponential minus a becomes 0, and this function of phi a becomes 1. This function has a shape like an S, so it's called sigmoid function. It has a nice property that when the input goes to extreme big or extreme small, the value of the output is constrained between 0 and 1 nicely. Also, this function is smooth, which is very useful when you try to figure out the rules to change the network parameters. Now let's consider how to build a training algorithm for neural networks. The output of our old friend, the ith neuron, in the Lth layer, write it as xi of L. Now, suppose that we know one magic value, which tells Which tells the effect of this neuron on the target value L. Okay, let's write it. What do we mean by the effect? I mean that if we change the output of this neuron by a small amount, very small, infinitesimally small, delta xli, and we know this factor that to reach the change in the target value L in proportional to the change in the output of this neuron X. Is of course in mathematical terms the derivative, the partial derivative of the target value L with respect to the output of this neuron. Let's write the partial derivative in a short form. This, okay. Now recall that the output of this neuron is the result of this nonlinear mapping here, and the input of this nonlinear mapping, or put it into other words, this nonlinear mapping brings the one value into the output, and this one value we use A to represent it. It's also the ith neuron and over the Lth layer, and A is just the collection of the input. So this is the previous layer, x minus 1, and that's x minus 1 p here, and the sum is weighted by those. The goal here is to pass this knowledge of how the change of this neuron affect the final objective function back. Specifically, we want to know what if we change the network parameters W here will affect the objective function L. We first to push this knowledge back one step to consider how the change in A affects L, which means which is a partial derivative of L with respect to A. Look, if we change x by delta, and the L will change by this amount. So what if we change A by delta? Now the change in x will be, and the change in L will be correspondingly multiplied by this factor. So the partial derivative of L with respect to A can be read as, and this computation is no other than the chain rule of computing derivatives. Now the knowledge of influence has arrived here. Now we are ready to compute the partial derivatives of L with respect to all these parameters. The influence on the target value of this A multiplied by the corresponding input. Now we know what will happen to the final target value if we change the width in this neuron. But remember, the whole computation starts from this presumed knowledge here. We know how, if we change the output of this neuron, the target value will change. So to apply this technique to the entire network, we need to pass this knowledge back to the neurons in the previous layer. Okay, those neurons here, if we want to know how to change their parameters or the width, we must know how the changes in their output affect the final output, the target value. Let us clean the writing a little bit. Now the problem is, we know the partial derivative of L given with respect to the pre-image of this neuron I. We want to know the partial derivative of L with respect to one of its or all of its input from the previous layer. And from this image, it's very clear that if we write it here, x of the previous layer G, that is just the partial derivative we already know of the pre-image of the ith neuron in the else layer multiplied by the corresponding weight. We must be reminded that this output is not only given to this one neuron. There are multiple neurons in the else layer. Let's consider, for example, there is another neuron. Say that is the kth neuron of the else layer. It also accepts the output of now this jth neuron of the L-1th layer, which is our interest. And here it is combined with a weight of the kth neuron of the th layer accepting the jth neuron from the previous layer. Okay, so the effect of these multiple connections means when we have a small change in this output neuron, all those pre-images and of course those outputs of the next layer, which is the layer L, will change. When we consider the influence of the output of this neuron, we must count all those neurons in this layer. We have sum over I, where I is in the I is over all the neurons in the else layer. Expressing this computation in matrix form, we have this formula. That is called a backpropagation. It's just a fancy word for the chain rule of doing partial derivatives. Next, we consider implementing neural networks using a computer program. There are a few points need to pay attention, like how to organize the computational resources, mainly the memories, to store the model parameters, and where the different objects has ownership to these resources, and how to organize a neural network structure in different objects. And of course, we need to pay attention to the algorithm itself. Let's show how to implement a basic neural network in Python with the help of NumPy. First, let us import the NumPy library p, and we can start coding by defining objects like a neuron. Right? However, in this way, although we can have a fine control of the behavior of each neuron, but as we have discussed, the computations in the neural networks are grouped into layers of neurons. All neurons in each single layer, they have similar behavior patterns. They share similar attributes. The computations are similar. So we start building neural networks by using what we call the layers as the building blocks. Then we do object called a basic layer. In Python, the constructor of one object are always named initialization. For each method, the first argument is a reference of the object itself. So for a layer to initialize a layer, we are concerned with two important information. One is the inputs, the number of inputs the layer of neurons collects. That number of inputs are shared by each single neuron in this layer, and the number of output of this layer. It is actually, if you think each neuron generates one output, that is the number of the neurons in this layer. Okay, as we discussed, the behavior of each neuron can be described by a group of weights, and collectively a layer of neuron can be specified by a weight matrix. Let's call it weight, and give it an initial value. Normally we take random values. The random module of NumPy provides a group of random generators. Now we take this particular one. It generates normal distributed values which have zero mean and unit variance of a given size. Normally we will normalize the weight a bit, but that is not our focus here. Okay, out, right. The most basic function of a layer is to process the information from the input to the output. Okay, this operation is commonly named forward. So it takes the input from the previous layer and let us store the input value which would be used later. And as we have discussed, each layer will compute the linear summation, the weighted linear summation from the previous layer. We will need this value, so we temporarily store it in this called A_ matrix. Use matrix multiplication dot self x and the weight matrix, and the output is just a linear map of this A. We call the outputs y, and that is 1 over 1 plus exponential minus A. Here we will find if we provide this utility function, it will make life easier for us later. E1x return 1 plus numpy exponential minus x. So here we just need 1 over e1 y. Sorry, dot a. Okay. So far for the basic information processing for this basic layer, and next we will build a basic net object. It collects a number of layers and link the operations, link the information processing operations from one layer to another layer. So that is the working horse of the neural network. Okay, its constructor takes. The constructor takes the configuration of each layers n units. Okay, and we start from build an empty list to store these layers. For each input number and output number, in using zip, we can take one element from two lists each, and then go over the two lists one by one. And now these two lists are in fact both sublists from the same n-unit list. That means from the first element to the second last one, including the second last one, but not including the very last one. And n units from the second element to the very last one. If we zip these two sublists together, let's see what will happen. Self layers append a new layer. The new layer is created by the basic layer as a basic layer object. It takes two input. One is the number of input and the other is the number of output. So if the n units come like the number of input of the number of variables in the input, number of variables in the second layer, the number of variables of the third layer, this n0, n1 takes the number of variables of the first layer, the second layer, then the second layer, the third layer, this third layer, and fourth layer, so on and so forth. This is because the output number of the number of outputs of the previous layer, it happens to be the number of inputs of the next layer. Okay. Then we do this collective forward function. It takes the net object to process the input from one layer to the next until the last one. Let's first have a token that is attached to the information, the bunch of information being processed. We will later find this is useful. For each layer, self.layers, we use this layer to perform forward, and this x underscore we just attached to the input. After this layer is done, we take its output for the processing of the next layer. Okay, when this loop is done, we can take the final output for the net. Okay, now we have finished the forward processing operation of a neural network. Let's try to use this network to do some basic processing. Okay, for example, we may have 10 samples. In each of the sample, we consider 5 input variables, which is the number of our x variables. Now this function initialized the random. Sorry, this is random. So this is a start. This resets the random number generator, so that in each of the core, we can from here on to guarantee that the random numbers it gives us are the same. Although it seems to be conflicting with the idea of being random, but this practice makes it much easier for us to check the bugs in the program. Okay, now this random generator has been initialized. We can generate our input and samples by n variables. Okay, now we will consider neural network. Let's have one hidden layer. And in the hidden layer, let's consider 3 hidden units. Now we can create a net object. Net. This is a list of the number of variables in each layer, n variables, n hidden, and let the output has only one variable in each of the sample. Right? Okay. Yes. Execute this cell. What happens? Right. We are now created a network object. Let's have a look. This is a basic net object. Okay. Let's use this basic net to forward or process our input variable. Before that, we may check the shape of the variable. Oh, it's 10 samples in each of sample. It has each row represents one sample and has 5 elements in that. So if we use the network to forward x, what we'll get? Have a look. Check the output of the network. Okay. Here is the output, which is a 10 by 1 a column-like matrix. The shape is 10 by 1. Because now the input data is not is just a randomly generated numbers. It doesn't have any meaning in them. So the best we can do is to check if the dimensions or the shapes of the output are as expected. Okay, it seems to be working now. In the next step, let us consider if we are provided with both the input variables and the desired target values. How to adjust the parameters of the net, which are the weight matrices of each layer, and so that the network produces desired outputs for the training data. Let us start by defining the backward function for each of the layer, which implements the propagation of the partial derivative partial derivative of the target value with respect to the output of each layer of neurons back all through this network. This backward function accepts the input argument of we call it partial derivative of L with respect to the output of this layer. Okay. Given the partial derivative of the object with respect to the outputs, we can first, by the chain rule of computing partial derivatives, we start from compute the partial derivatives of the element that is closest to the output, which is the partial derivatives with respect to the linear summation. Because between the linear summation and the output of the layer, there is only one nonlinear function. So the partial derivatives with respect to the A matrix is just the partial derivatives given to us, which is respect to the output, multiplied by the derivative of the object with respect to A. So D, which is dl over dA equals dl over dy multiplied by dy over dA. This d is means partial derivative, of course. And the derivative of the sigmoid function, if you believe me, has a form of this. It is exponential of minus a, which is the E1 function minus 1, in fact, divided by the square of the E1 function, which is 1 plus exponential minus a. And another time. Sorry. Okay. Right. And the next step is to compute the partial derivative of L with respect to the parameters of this layer. That is the ultimate target of this backpropagation, because those parameters are what we need to change, adjust in the learning process. Is if we recap of the computation derivation we had when discussing the network, it is like this. The matrix product between the transpose of the input and the partial derivative of L with respect to the linear summation. Then the next task is to pass the information of how the element in this layer affects the loss function to the previous layer. We call it partial derivative of L with respect to x. X represents the input of this layer. Yes. According to our derivation previously, we have this matrix production. The partial derivative of L with respect to A multiplied by the transpose of the weight matrix of this layer. Okay, and now we define another function which called update, that is just to adjust the W matrix according to the computed partial derivative of L with respect to W. This function takes an argument called learning rate, because we only consider the first order derivatives, and there is so which means if we take infinitesimal move, the object function will move accordingly. However, we are not actually taking infinitesimal move. We take the step of some size. If we move to a particular by a particular size, and if the size is too big, the partial derivative, the first order derivatives will cease to be effective. So here is actually a step size parameter for adjusting the width. What we do is to give the update rule of this layer. Return. Sorry, it's adjust the weight function, weight matrix by the partial derivative, and scaled by this learning rate. Take care, this is a minus sign, because we want the objective function, which is the loss, to be as small as possible. For the entire net, the backward function is just to link the backward operation of each of the layer. Okay, and the input of the backward function is interesting here. We use the ground truth target value to start the computation of the error functions. But to have the input, to have the ground truth of the target value to act as a guide to which function we should adjust the parameters, we should first define a loss of this net. Okay. Now let's have an extremely simple loss. If the functions, the network's output is y, we compare it to the ground truth y. The comparison is taken like that because the ground truth y is either 1 or 0, it's a binary value, and the predicted y is some value between 0 and y. Remember, it is the output of the sigmoid function of the last layer. We hope if the ground truth of a sample is 1, we hope the output of the y value, the prediction of the network for the same sample, to be as close to 1 as possible. Okay, so here, if the ground truth y is 1, the loss we would like to be the difference between 1 and the prediction. Remember that the prediction is generated by a sigmoid function. It will never exceed 1. It will always be smaller than 1. So if this guy is 1, we want this loss. Means if the prediction closer to 1, the loss is small. If it's close to 0 instead of 1, the loss will be big rate. And on the other hand, if the ground truth is 0, we would like the prediction to be as close to 0 as possible. Now we have the prediction value itself as the loss. So if the ground truth is 0, the closer to 0, the smaller the loss. The closer to 1, the greater the loss. And overall, this term, the ground truth y and 1 minus ground truth y, acts like a switch. If ground truth is 1, this switch is off. This switch is on, and the loss is taken as 1 minus the prediction of the net. If the ground truth is 0, this switch is off and this one is on. And the loss is defined as the predicted y value. It should be as close to 0 as possible. We take all of those together and sum them over all the samples and return the loss. Okay, now back to the backward propagation operation. If the loss is defined as this function, the derivative of the loss with respect to the final output of the network can be written derivative as this. If you do the math, this will be the partial derivative. Now we have the partial derivative of the object or the loss function with respect to the output of the last layer. Okay, then we can do the backpropagation by iterating from the last layer till the first one layers. We call the backward function of each of the layer, and when the backpropagation of one layer is done, we take this partial derivative with respect to the output, take that derivative to the how is the partial derivative with respect to the output of the previous layer of the current layer. Okay, here is our backward propagation function of the neural network. To update the width of the neural network, we just write the update function, and it is a wrapper of the individual layers update function. Okay, now we finish defining the basic neural network. So let's test our network. First, we make a basic solver object, which is just a housekeeper to help us to create a network and take care of the training steps, like how many iteration steps it takes, and when to stop, what is the learning rate, stuff like that. If we load the data we used in our last lecture. That is the images of the digits. But instead of handcraft the two-dimensional features for the data, now we let the neural network, the first layer of the neural network, has exactly the same number of pixels as the neurons, and that the neural network has two hidden neurons in the second layer, which we hope that the network will pick up relevant features for the classification task. And now let's see what happens. Let's take this small learning rate and let the maximum iteration to be 100 times over the data set. Okay, have a look. Right, the network arrives to zero training errors. We must be reminded that is a training errors does not necessarily mean that we have a good model to predict the data, but at least it shows the training algorithm works. And another notice to be taken is that the loss is not necessarily the same as the training errors. For the loss, to have the backward propagation algorithm works, we need to compute the partial derivatives, for which we need some manageable loss, preferably some smooth mathematical mapping so that we can compute the derivatives easily. But the number of error predictions in the training data is a binary 0-1 loss. That is in fact one essential difference between linear models and neural networks and the perceptrons we have introduced in our last lecture. In perceptrons, the loss itself is the number of errors itself, but in neural networks we need some numerical loss. So much for the training of neural network algorithm. We have shown the implementation and the working flow of a very simple neural network. But if you notice, there is a very subtle gap in our reasoning in the implementation of the backpropagation algorithm. Actually, the goal in each iteration of the optimization or training of the model, we would like to know how to adjust the model parameters W. But in fact, the partial derivative the model actually computes is not the change in W, but how the change in L if we change W in a specific way. That is because, of course, you can change the W and derive in a different hypothesis of a neural network in whatever way you want, as long as you can make the loss function smaller than the previous step. But if you take the a near-sight view of that, you can choose the most effective way to do that. I recount here, I emphasize here, this is a near-sighted view. Because we take the first order partial derivative. Consider you are on a terrain, a rugged terrain. You want to go to descend as fast as possible, and in each step you take a certain step size. You can only travel a certain amount of distance in each step. So how to make your step count? The way is to choose a direction along which the terrain goes downhill fastest. And if you travel along that direction, in the near future, you are traveling in the most efficient way. Okay, that is called a gradient descent, and it's a very popular method in learning models. And but as we have just said, that is the first order derivative implied inducted method. Perhaps the fastest descending direction changing rapidly as you travel. As long as you travel a small step, the direction change dramatically, and the direction you have chosen is no longer being the most efficient one. So in practice, you have many choices in implementing the training algorithm. Like you can choose the step size, normally we call that learning rate, or you may want to keep your momentum to traveling along some certain direction without being disturbed by the small fluctuations of the terrain. You can have a momentum. There are many studies in literature to talk about this topic. Then we continue talking about the generalization issue we left from last lecture. What if we have multiple hypotheses that makes the Houghton inequality doesn't guarantee anymore that we have small derivation when we measure the errors of the hypothesis on the training data set? We first introduce a very intuitive and simple scheme to consider how to generalize a hypothesis chosen by a learning algorithm. In a practical procedure, let us consider more carefully where is the randomness of the difference between in-sample error and out-sample error comes from. Consider this space, which represent joining n samples from the entire data population, where the randomness is driven by the joining n samples, this random process. So each element or each point, if you like, in this space represent a data set of n samples. For example, this one we may call it data set 0, which is consists from of like sample 1 of dataset 0 until sample n of dataset 0. Okay, this may be dataset 1 and of sample 1 of dataset 1 until sample n of dataset 1. Of course, in practice, you may not always be able to count the data set one after another. They may be in most cases this will be a continuous space, but you get the idea how the points in this space represents. Now, given some hypothesis H and some tolerance of epsilon, and we can call each of the points in this space good or bad. Remember, each point represents n data sample. The good point is with respect to the chosen hypothesis and the tolerance. That is the in-sample error measured. The in-sample measure evaluated for this hypothesis on a good data point on a good data set deviates from the true out-sample error of that hypothesis is smaller than the tolerance. And of course, the bad data sets of this hypothesis and tolerance is means the difference between the in-sample error measured on this bad dataset deviates from the out-sample error greater than by some value greater than epsilon. If we color each of the bad point using, for example, red. Previously, we have the Hofstadter inequality, saying that if we think the area of the entire space as 1, the area of the red region, of course, it can be like disconnected regions scattered all over the space, but for simplicity, we can consider it as we join it in this single region here. The area of this bad red regions can be made very small by enlarging the number of samples in the dataset. And our problem is that we have multiple hypotheses. Recall that the bad area is with respect to that specific hypothesis. So in our colors in this illustration, actually for each individual hypothesis, we have a different coloring scheme. So if you color the space using all these different hypotheses, eventually you will end up with the bad region, which is the colored region, much larger than the guarantee you want to have. One way to solve this problem is intuitive. It is very natural. If we would like the total area of the bad areas, bad regions, to be smaller than some threshold C, we can choose N so that the Hofstadter inequality says that the area of the bad region for individual hypothesis is smaller than C divided by the number of total hypotheses. In this case, we can add the bad area together, and eventually we have the total area of the bad regions smaller than the chosen threshold C. More specifically, let's consider the event that our training data set is bad for any hypothesis in the hypothesis candidates, capital H represented by here. That event is equivalent to saying that the data set is bad for H1, or it is bad for H2, so on and so forth, or it is bad for HM, and M is the total number of hypotheses in the hypothesis candidate set. If we consider the probability of this event, we can see that the probability D is bad for any hypothesis in capital H is smaller or equal than the probability of it is bad for event hypothesis 1 plus that for hypothesis 2, and go all the way to the probability it is bad for hypothesis HM. And by Hofstadter inequality, for each of these individual hypotheses, we can bound the chance by C divided by M, and then when we sum all this over, we have the total chance of D is bad for any of the hypotheses in H, smaller or equal than C. Next, we will see why the scheme we just discussed won't work for practical cases, and how to deal with it. However, in practice, the intuitive solution of increasing the sample number to shrink the Hofstadter inequality so that the bound is accounting for the total number of hypotheses will not work, because Most of the practical data learning algorithms are in fact chosen not from a limited number of hypotheses, but exploring an infinite hypothesis space. Considering that the perception, in the simplest perception, we have two parameters, W0, W1, which makes the hypothesis set which has the hypothesis set that is corresponding to the square of the real number space. That is the infinite space and corresponding to infinite hypothesis. So when m goes to infinite, there is no guarantee that we can shrink the Hoffding inequality C over m to 0, and to guarantee that we have the total bed area of the bed regions smaller than C. Consider that in this way, if we have infinite number of bed regions, all those regions will cover the random space quite quickly. Even you can shrink each of the individual region to be very small. When you sum them together, you have no theoretical guarantee that the infinite summation will be small as well. The solution towards this problem, let us first explain that intuitively. The intuition is that by counting the bed region for each individual hypothesis separately, we over-account much of the bed areas. Hopefully, one hypothesis in the hypothesis set will have many similar ones to it. So the actual coloring of the random space has many overlaps. And in these overlaps, we have hope that if we count this overlap together, we may have limit the bed area in some bounded region. For example, for the perception model, consider how the hypothesis dichotomize or separate the space of the data. It is not difficult to imagine that there will be many similar hypotheses, and the good and bad region for those hypotheses in the unsample random space should have much overlap with each other. So much for the intuition. Let us consider the sketch of the proof. We begin with some probabilistic logic of derivation. Consider that if we would like to bound the probability of some event B, consider the element of B in a random space. If we have B leads to some other event C, and consider the element in the random space that makes B. If B implies C, we have that each element in B must be also an element in C. That is if B implies C. Okay? So we can see that B is enclosed by C. And in the language quantitatively, we see the probability of B is less than or equals to C. An intuitive way of think this way of reasoning is that if we would like to consider some event that is not directly under our control or that are not directly measurable, we may alternatively consider the chance of a necessary consequence of that event. If we can somehow bound the chance of the consequence is going to happen. Now, by a reverse logic, we simultaneously guarantee that the cause shouldn't be happening with a chance larger than the chance of the consequence is happening. Now, let's consider a more sophisticated case in this line of reasoning. What if B, what if B doesn't imply C? In this case, we cannot directly bound the probability B using probability C, because there is no guarantee is whatever inside B is included by C. In this case, the next best thing we can expect is that the probability of C is happening given B is guaranteed to be larger than some threshold or constant. We call it Fc. Now consider the random experiment outcomes in event B. In this space, the threshold we have, that low limit we have for the conditional probability, means that the chance when B is happening, the chance that C is happening as well is at least of Fc. So if we mark that region using a shade, that means the area of the shaded region over the area of event B is at least Fc. If we have this at hand, could we somehow to bound the probability of B using that of C? Consider basic probability equation that the chance of the joint event B and C equals the probability of B multiplied the conditional probability of C given B. Since the conditional probability is at least Fc, now we can bound the probability of B using the probability of the joint event B and C divided by Fc. Furthermore, if the event B and C are both happening, implies some event D. That means the probability B and C is bounded by the probability of D. Okay, in this case we can push this relationship further, say that the probability of B is less than or equal to the probability of D, and which is divided by Fc. Back to our problem. Let's have the event B, which is called bad event. That is for in our hypothesis set, there is some hypothesis in this H. Okay, so that the error evaluated for this H using our dataset D deviates from the true outsample error of H larger than by some value larger than epsilon. Now, if B is the case, we must span this sum H. Let's call one of such H cross. Now we have E in H cross on dataset D deviates from the E out H cross by an error larger than epsilon. Now consider an event C, where C is in particular for this H cross, and we let it we sample another independent set of n samples, which is kind of duplicate the sampling process of the data set. But we do the resampling completely independently. We call it dataset D prime, and let the event C be that the in-sample error evaluated for data cross on D prime. Let's mark here. This is a D prime in-sample error. The difference between this and the E out H cross, this is the same. Let the difference is smaller than half of epsilon. Okay, now let's have a look of these errors on geometrically in a more intuitive way. See, that is E out H cross. This is the center, and so even in event B, it is determined that the in-sample error of H cross valued on the original data set here falls in these two regions, which is away from the E out by at least epsilon. Okay, and this event C means the E in error on H cross measured by D prime is within this region, which is deviate from E out within half of epsilon. So when putting together, B and C implies some event D, and that event D we can write as the in-sample error of H cross measured by the original data set. Take the difference between this one and the in-sample error of H cross measured on D prime. The difference between these two in-sample errors is exceeding half of epsilon. We say C means this in-sample error in this area, and B means this in-sample error is in this area. Whatever the distribution of these in-sample errors, they are separated by at least half of epsilon. Okay. Now apply the technique of bounding B using event D we have discussed above here. We have the probability of B is bounded by 1 over some Fc, where Fc is some threshold value where the probability of C given B exceeds that value by the probability of D. And by the Houghton inequality, because the event C is respect to a particular hypothesis, a single one, H cross, so that can make Fc approaching 1. And that means 1 over Fc will not be a very big value. See, it is as see, we can make it as a constant, for example, at most 2. Now we can bound the probability of the bad event B using the probability of the bad event D. So where is the big deal? Why we change our focus from limiting the in-sample error within some range of the out-sample error into consider the chance of this bad event D, which means the in-sample error on two independent data samples are different from each other very much. What have we achieved? Did we make the problem simpler? Yes, indeed we do. Because look at the event D doesn't depend on the unknown E out, for which the diversity of the hypothesis set on the entire data set is very difficult to gauge. We consider the difference in these two data samples, and we can somehow limit the diversity of our hypothesis set on finite number of samples, as long as the diversity of our hypothesis set does not grow as much as the number of samples in these two data sets. By another Houghton inequality, we can bound the difference between bound the chance of having large difference in sample error on these two data samples. And in this indirect way, we bound the chance of having larger difference between the in-sample and off-sample errors on a single data set. That is a significant achievement of a learning theory.